lecture we saw what is the maximum and minimum of a function. Okay. This time we'll talk about what is the local maximum and local minimum. So suppose f is a function and a set A belongs to the domain of f. Domain of f, A is a subset of that. Then x in A is called a local maximum of f, is a local maximum of f if there is some neighborhood of f where it is the maximum. If there exists delta greater than 0 such that x is a maximum of f on A intersection x minus delta to x plus delta. Similarly, x in A is a local minimum of f if there exists a delta greater than 0 such that x is a minimum of f on A intersection x minus delta to x plus delta. We saw theorem 1 say that, if the derivative exists at a maximum or minimum, then the derivative has to be 0. In fact, the same is true for local maximums and local minimums. Theorem 2. If f is defined on AB, f defined on AB and has a local max or a min, local max / minimum at x in AB, and if x is differentiable at x and f differentiable at x, then f prime at x is equal to 0. I mean, you have seen that this is true for in Calc 1, right? If you're doing the if you're looking at a small neighborhood, when you take the derivative, it's 0. And the proof is exactly the same. Exactly the same as theorem 1. In fact, you can get it from theorem 1. Proof from theorem 1. From theorem 1, right? If it's a local max or min, you look at the small interval x minus delta from theorem 1 on x minus delta to x plus delta. You look at this small interval, it is the maximum there, therefore the derivative has to be 0, or it's the minimum there, so the derivative has to be 0, right? And so this is more or less a direct application of theorem 1. However, you have seen that the other way is not true. In case you don't remember from Calc 1, however, f prime of x is equal to 0 does not mean local max or min, right? Min. Standard counterexample that's like the easiest one is function f of x is equal to x cubed, or any odd function of frankly. F of x is equal to x cubed. F prime of x is equal to 3x squared. Therefore, f prime of 0 is equal to 0, but 0 is not a local max slash min. Right? In general, it's not a local max or a min on any interval. If I take, for example, -1 to 1, the derivative at 0 is still 0, but it's not a local max or min in the interval from -1 to 1. Okay? So now let us look at the first major theorem, which is significantly different than what we have done before. Like, we will look at theorem 3, Rolle's theorem. Theorem 3, Rolle's theorem. What we call as the mean value theorem is a direct application of the Rolle's theorem, is a direct consequence of the Rolle's theorem, and we will look at it afterwards. Okay, but here's the statement of Rolle's theorem. If f is continuous on a to b and differentiable on at least open interval a to b, with f of a is equal to f of b, then there exists, or there is a number x in AB such that f prime of x is equal to 0, right? Now, proof. This is a slightly different statement. We are not frankly saying that, oh, there's a maximum or a minimum, but that is what we will be using in this proof. So, if my function f is continuous on a to b, then it's on the closed interval a to b, then I know that it has a maximum in the interval a to b. If f, not exactly, as f is continuous on a to b, there exists x in a to b such that f of x such that x is the maximum. X is the maximum, right? Now, if it is not on the endpoints, if x is in small a to b, sorry, not small, is in the open interval a to b, which is not the endpoints, then by theorem 1, f prime of x is equal to 0 as required, right? Now, suppose the minimum is somewhere. Suppose the maximum is at an endpoint. Suppose max of f is a or b. Okay, so assuming that the maximum lies at a or b, look at the minimum. Look at minimum of f on a to b. Once again, if the minimum is inside a to b, call it maybe y. If y is in the open interval a to b, then again by theorem 1, then by theorem 1, once again I get that f prime of y is equal to 0 as required. Now, suppose the minimum is also one of a or b. If the max and min are both at a or b, then because I assumed that f of a is equal to f of b, then as f of a is equal to f of b, the max and min are equal. The maximum value is equal to minimum value, right? And the only way that can happen is if my function is constant. Therefore, f of f is a constant function. And therefore, f prime of x is equal to 0 for every x in AB, right? Therefore, in either of the cases, I have found some x such that its derivative is 0. Okay? Now, we will use Rolle's theorem to prove mean value theorem. Of course, it is a special case of mean value theorem, but I can also use Rolle's theorem to prove mean value theorem. So, in case you don't remember what mean value theorem is, theorem 4, mean value theorem. What does the mean value theorem say? If f is continuous on AB and differentiable on open interval AB, then there is a number x, then there is a number number x in AB such that f prime of x is equal to f of b minus f of a over b minus a, right? The mean value of the derivative is achieved, and it is quite easy to see that, oh, the Rolle's theorem is a direct consequence of the mean value theorem, right? Rolle's theorem says, oh, if f of a is equal to f of b, then, well, f of b minus f of a is 0. So I get f prime of x should be equal to 0, which is what my Rolle's theorem said. Oh, there is some number where the derivative is 0. How do I prove mean value theorem using Rolle's theorem? Well, let us consider a function h of x is equal to f of x minus f of b minus f of a over b minus a times x minus a. Okay. So what is happening now? Therefore, h of x is equal to h of a is equal to, what happens if I put f of a, if I put a, f of a minus f of b minus f of a over b minus a, all times a minus a, which is equal to f of a, right? And h of b is equal to f of b minus, well, let me write this properly, my bad, this a looks ugly. A, right? F of b minus f of a over b minus a multiplied by b minus a. Well, the b minus a is cancel, and I get f of b minus f of b plus f of a, which is f of b minus f of b plus f of a is equal to f of a. So I do have that f of a, h of a is equal to h of b, right? Therefore, h of a is equal to h of b. And what is the derivative of, well, let me not get ahead of that. Therefore, by, okay, let me first show this. H prime of x is equal to f prime of x plus, well, f of b minus a over f of b minus a is a constant, minus f of a over b minus a times derivative of x minus a is just 1, okay? And so this is just f prime of x plus f of b minus f of a over b minus a. Therefore, by Rolle's theorem, because h is differentiable everywhere and h of a is equal to h of b, I get, therefore, there is a point, there exists x naught in AB, x naught in A to B, such that, sorry, this should be x naught in in A to B, such that 0 is equal to h prime of h prime of x naught is equal to f prime of x naught plus, my bad, this should have been a minus, minus f of b minus f of a over b minus a. Okay, and so therefore I get that 0 is equal to f prime of x naught minus f of b minus f of a. Therefore f prime of x naught is equal to f of b minus f of a over b minus a. And that concludes my proof of the mean value theorem. Okay, so let's stop here for this video.